Training a massive frontier-scale model hinges on the surgical precision of global batch sizes and per-layer learning rates. Before the first iteration begins, these variables must be defined to prevent the entire architecture from collapsing during the training run. This log-log plot reveals the central engineering challenge. Under standard parameterization, the default setup for most neural networks, as the model width increases along the x-axis, the optimal learning rate curve strictly shifts downward on the y-axis. Selecting the wrong learning rate at the 7 billion parameter scale wastes thousands of dollars. But executing a brute force sweep on a 400 billion parameter architecture costs tens of millions. At this scale, direct hyperparameter optimization is no longer viable. To bypass this compute bottleneck, researchers use proxy scaling, running exhaustive sweeps on miniature surrogate models, extract the optimal parameters, and project those settings up to the target scale. Modern labs rely on two specific paradigms to ensure those settings actually transfer. They either deploy rigorous empirical extrapolation, seen in models like DeepSeek and Mini-CPM, or they engineer mathematical scale invariance directly into the network through Maximal Update Parameterization, or MUPUP. Succeeding at the frontier requires either exhaustive empirical tooling or strict mathematical interventions to predict the optimizer's trajectory without guessing. DeepSeek V1 exemplifies the empirical approach. Their engineering teams execute direct, exhaustive grid searches over batch sizes and learning rates, entirely restricting these compute-heavy sweeps to small proxy models. By plotting these localized optimal points, they fit a scaling law line. This mathematical projection allows them to calculate the exact learning rate required for their target 67 billion parameter model, bypassing the need for a full-scale grid search. Even with the learning rate optimized, researchers face a separate bottleneck in the Chinchilla scaling laws, specifically regarding how standard cosine decay schedules prevent the reuse of training checkpoints. A cosine decay curve is rigidly tied to the total target step count. Because the slope of the cooldown phase is locked the moment training initiates, you cannot extract a checkpoint halfway through the run and evaluate it as a completed, smaller model. Measuring how varying amounts of data affect the final loss forces teams to execute complete, independent training runs from scratch for every single token count target, creating an ON-squared explosion in compute costs. Running thousands of redundant proxy models rapidly exhausts compute budgets. Extracting accurate empirical scaling data at the frontier requires an entirely different approach to learning rate scheduling. The traditional parabolic cosine curve is replaced by Mini-CPM's warm-up stable decay, or WSD schedule. This geometric trapezoid features a long, flat stable phase and rapid decay. Because the stable phase is uniform, the decay sequence can simply slide to an earlier checkpoint. Engineers train a single proxy model along that flat stable line, save checkpoints at various token intervals, and apply the rapid decay phase backward to each saved state. This extracts dozens of complete Chinchilla scaling points from the cost of a single comprehensive run. With isoflops analysis optimized, modern labs aggressively execute proxy sweeps. This intense empirical testing revealed that the original 20-to-1 Chinchilla token-to-parameter ratio actually leaves significant performance on the table. This chart tracks the evolution of data efficiency. While the original Chinchilla baseline sits at 20-to-1, extensive proxy testing drove Meta's Llama 3 to operate at a 40-to-1 ratio and pushed Hunyuan Large to 96-to-1. These empirical proxy techniques also validate novel architectures. Minimax 01 charted lower envelope loss curves across small-scale models to justify the viability of linear and hybrid attention mechanisms at scale. WSD schedules produce immense efficiency for proxy sweeps, yet they remain a reactive workaround to the core instability inherent in standard model parameterization. Cerebras GPT applies an entirely distinct method. Instead of empirically chasing hyperparameter drift, they mathematically pin the hyperparameters at initialization to ensure they never move. To stabilize a linear network as its width expands, we mathematically pin the initial activations to a bounded constant, theta of 1, by scaling weight initialization to the inverse square root of fan n. A single gradient step update must also remain bounded. Structuring the gradient calculation as a rank 1 update, we map the product of the previous layer's norm against the operator norm of the weight change. Isolating these terms lets us solve directly for the learning rate target that satisfies both bounded constraints. For standard SGD, the optimal learning rate strictly equals fan-out divided by fan-in, but for the Atom optimizer, the scaling rule shifts. To maintain scale invariance, Atom's optimal learning rate must be exactly proportional to 1 divided by the fan-in dimension. Standard parameterization assigns a static, global learning rate, which destabilizes the network as it widens. Maximal update parameterization scales every layer's individual learning rate by 1 over its width, mathematically freezing the optimal learning rate across all architectural scales. This test loss plot from the Cerebras GPT runs validates the derivation. Look at the blue line tracking standard parameterization. Unstable learning rates cause the data to oscillate around the predicted fit line. Now observe the orange mu-pup line, adhering strictly to the predicted scaling path. The engineering advantage is immense. Researchers tuned their proxy models at a 40 million parameter scale, and those exact hyperparameter targets transferred without adjustment up to a 13 billion parameter architecture. Independent ablations prove the math holds across modern architectures. The 1 over width transfer remains stable even swapping in Swiglu nonlinearities, scale-up global batch sizes, or zero-out query matrices. However, strict mathematical derivations carry absolute boundaries. If you alter the core flow of the optimizer or normalization layers, the mu-pep derivation fails entirely. The transfer mechanism shatters if you deploy exotic optimizers like Lion, which rely on the sign of the gradient rather than its magnitude. It also breaks if you apply heavy weight decay or introduce learnable RMS norm gains into the architecture. At the 400 billion parameter scale, empirical WSD schedules and the mathematical anchors of mu-pep determine whether a run succeeds or collapses. These methodologies represent the core engineering playbook of 2025's Frontier Labs. If you want to dive deeper into the mathematics and engineering behind frontier models, subscribe to the channel and listen to our